Now that we've talked about resistors in series and how to combine them, let's look at more series circuits with resistors and derive the equation for a voltage divider. So suppose we have a simple series circuit with just two resistors in series. So I'll let this be R1, I'll let this be R2. We'll have a voltage drop across R1 of V1 and a voltage drop across R2 of V2. Now, by KVL, remember from the last video, if we start in an arbitrary place in the circuit and we go around, as long as we follow the passive sign convention and add up all of the voltage drops, we should get 0. So KVL tells us that negative Vs plus V1 plus V2 is equal to 0. Now, an implication of KVL is that series resistors act as voltage dividers. So that means that whatever the source voltage that's being applied to our series circuit is, that will be divided amongst V1 and V2. Not necessarily equally, because these resistors might not be the same value, but if we add V1 and V2 up, it will equal Vs. So what else do we know about series resistors? So for resistors in series, we saw last time that R equivalent is given by just adding up the resistance values, plus R3 dot dot dot, however many there may be. And we also have Ohm's law. So by Ohm's law, which says that V equals IR, in our circuit here, we have Vs is equal to the current coming from the source times R equivalent. Okay, great. So that means I can rearrange terms to give me Is is equal to Vs over R equivalent. Now, for this example here, our R equivalent is just going to be R1 plus R2 because we only have these two resistors in series. So this is Vs over R1 plus R2. Okay, great. So once you have your I source is going to be the same current that goes through R1 and the same current that goes through R2. Since it's a series circuit, there's no nodes or branches, and so the current is going to be the same everywhere. So that means at the first resistor, the voltage drop across resistor 1 is going to be given by Ohm's law, Is times R1. Is is the current that's coming out of the source, but it's also the current that's going through R1 because it's a series circuit. Okay, great. So then if I take this equation here and I plug it in for this Is, this is going to give me Vs over R1 plus R2 times R1. Okay, great. So I'm going to rearrange these terms so it looks like this. Vs times R1 over R1 plus R2. Now this thing here, this term is just a resistance divided by a resistance. Resistances are just going to be constants, right? So if you take a resistance divided by another resistance, this is going to give you another constant that's going to multiply our Vs. So we call this our scale factor. We call it the scale factor because it scales Vs. So that means we're going to take some constant, right, some fraction here, multiply it by Vs, and that will scale the source voltage, and that's going to give us our voltage drop, V1. Similarly, we can do the same derivation for V2. So V2 is just going to be Vs times, this time, instead of R1, it'll be R2 over R equivalent, R1 plus R2. Okay, so these guys here are the voltage divider equations. All right, so what's nice about these is that you get to skip the step of computing R equivalent and using it to find the current. Because as you can see, these equations here, we don't need current in order to find the voltage drop V1 and V2. All we need is just the resistors and the source voltage, and those resistors will scale our source voltages. So then let's do an example. So suppose we have a similar circuit, but this time let's say we have 3 resistors in series. Let's let our source voltage be 10 volts. Our R1 is 3 ohms. Let's let our R2 be 5 ohms. And let's let our R3 be 7 ohms. Okay, great. So then the voltage drop across R1, let's just call that V1. Voltage drop across R2, we can call that V2. And the voltage drop across R3, let's just call that V3. Okay, so this is a series circuit. We can find R equivalent by the equation of how to combine resistors in series. That's just going to be R1 plus R2 plus R3. So for our example here, that's 3 plus 5 plus 7, which gives us 15 ohms. Great, so we have our R equivalent. Now, let's use the voltage divider equations to find the voltage drop across all of these resistors, V1, V2, and V3. All right, firstly, V1, that's given by Vs times, we take R1 and we divide by R equivalent. So for our example here, Vs is 10 volts, R1 is 3 ohms, and R equivalent is 15 ohms. So our ohms are going to cancel. This just gives us 3 over 15. So if we multiply that by 10 volts, we're going to get 2 volts. Okay, secondly, V2 is Vs times, this time, R2 over R equivalent. So in our example here, that's 10 volts times 5 ohms over 15 ohms. The ohms cancel, and we get 5 over 15 times 10, which gives us 10 over 3 volts. And then finally, V3 is Vs times, this time, R3 over R equivalent. For our example, that's 10 volts times 7 ohms over 15 ohms, which gives us 14 over 3 volts. Great, so then it's a good idea to do a KVL check just to check all of your math. So our KVL check, to make sure if we start at this point in the circuit and go all the way around, adding up all the voltages and keeping straight our passive sign convention, we should get negative 10 plus 2 plus 10 over 3 plus 14 over 3. So that's going to give us negative 8 plus 24 over 3, or negative 8 plus 8, which is equal to 0. So our KVL check works, and that's how we use voltage divider equations to find voltage drop across resistors in series.